Hi everyone. I'm glad to show our work accepted by CVPR 2026. MotionCrafter, Dense Geometry and Motion Reconstruction with a 4D VAE. We propose the first video diffusion-based framework for joint geometry and motion reconstruction. Given a monocular video as input, MotionCrafter can achieve dense 4D scene reconstruction in the world coordinate system. This 4D representation includes both point cloud and scene flow for each frame, which stands for the geometry and motion, respectively. As a result, we can use this unified 4D representation to accurately describe a 4D scene. And it is convenient to extend it to downstream applications such as embodied AI. Our work answers this question. How much do the video diffusion model know about the 4D world? Transferring knowledge from a video diffusion model to 4D reconstruction is a non-trivial task. However, this task is promising because we can use a vast amount of cheap data to train a robust video diffusion model. This can alleviate the problem of expensive annotation acquisition for 4D reconstruction. To meet this challenge, we start with training the VAE to construct latent representations of geometry and motion. First, we consider the geometry VAE training. The input and output are the same, a world-centric point map sequence. And the main challenge lies in how to fine-tune an existing image VAE into a geometry VAE. To answer this question, previous work Geo4D proposed fixing the VAE encoder and fine-tuning the VAE decoder. Plus, they applied max rescaling to align the point cloud distribution with the original image. However, even with this alignment, discrepancies still exist in the distribution of the point clouds due to their unbounded nature and varying scales. This could lead to the loss of critical information during the encoding phase. Therefore, we investigate a fundamental question. Is strict alignment with the original distribution necessary for encoding the geometry? Considering the unbounded nature of point clouds, we propose to use mean rescaling to balance the scale differences and simultaneously fine-tune the VAE encoder and decoder. Through experiments with geometry VAEs, we found that using fixed VAE encoder with max rescaling works well in indoor scenes, but poorly in outdoor scenes. Even fine-tuning the VAE decoder like Geo4D struggles to recover the outdoor geometry. However, by applying mean rescaling and fine-tuning the entire geometry VAE, we found that the impact of this scale difference is significantly mitigated. Therefore, we draw an important conclusion. For modalities like point clouds, which differ significantly from image distributions, it is unnecessary to forcibly align the data distribution to inherit the prior knowledge of VAE. Furthermore, we confirm this in subsequent UNet training, where our proposed training method consistently improves the performance of both the VAE and UNet. Another important contribution of this paper comes from the unified encoding of geometry and motion. We represent geometry and motion using world-centric point maps and scene flows, respectively. Note that the scene flow here differs from the traditional definition of scene flow. Traditional scene flow is typically defined in camera coordinates, so any camera movement will affect the camera-centric scene flow. However, defining scene flow in world coordinates avoids this situation without explicitly predicting camera movement. Finally, we merged the geometry VAE and motion VAE into a single 4D VAE. Furthermore, we found that using a concatenated 4D latent to decode motion yields better performance. In summary, our 4D VAE offers the following advantages. 1. Define a unified 4D latent containing both geometric and motion information. 2. Output a dense 4D description for the state of each pixel. 3. Support for encoding and decoding unbounded values. In UNet training, like MotionCrafter, we support two training paradigms. The first is the denoising paradigm, which involves adding noise to the 4D latent and training a multi-step denoising UNet. The other approach is the deterministic paradigm, which directly predicts the corresponding 4D latent from the video latent. We found that this paradigm outperforms the denoising paradigm, likely because 4D reconstruction is a regression task rather than a generation task. Furthermore, this paradigm requires only single-step inference, resulting in faster inference speed and more stable inference results. We collected 13 synthetic datasets for training, including 3 datasets with motion annotations. In zero-shot generalization of real-world scenes, our results are more robust than other methods like Star Trek. Specifically, we have more reasonable geometric details and cleaner scene flow predictions. We also provide an interactive viewer based on Visor that clearly visualizes the geometry and motion of a scene for qualitative comparisons. We've open-sourced our code and weights on GitHub and Hugging Face. Feel free to visit our project page. Thank you for watching.